Ever feel like you're just swimming in information?
Yeah.
So much out there, right? And sometimes you just wish there was a shortcut, like a way to instantly get the really complex stuff.
Yeah, totally.
Well, think of this as maybe your cheat code. Welcome to the deep dive. We try to take those big piles of research and analysis and pull out the bits you really need to know.
And today, wow, we're diving into something really cutting edge. It's all about how we're teaching AI to understand the world. Well, more like we do, not just words, but seeing, hearing, watching, the whole picture.
Right.
We've got a great collection of research here, including a pretty recent paper that maps out this incredible journey of what they call multimodal reasoning models.
Multimodal reason. Okay, let's unpack that. Sounds a bit technical, maybe?
A little, yeah.
But it's really about AI making sense of, like, different kinds of info at the same time.
Exactly.
You know, like when you read a news story, you might also see a photo, maybe watch a video clip. Your brain just kind of puts it all together, right, for the full picture. So we're trying to get AI to do that. Connect text, images, audio, video, all of it.
That's precisely it. And our goal today, really, is to trace how these AI systems, these models, have learned to do this. We want to see, where do they start? What amazing things can they do now? And importantly, where are the real breakthroughs happening? It's quite a story. Lots of clever thinking.
Okay, so take us back, the beginning. How did AI even start trying to tackle this, understanding different types of information?
Well, for a long time, the approach was very segmented. You'd have different parts of the AI system, different modules, basically, designed just for specific data types.
Oh, okay.
So one part looks at images, another processes text.
Yeah.
And language was often the main focus.
Yeah.
Other senses were almost like afterthoughts.
Like having different tools in a toolbox, but they don't really talk to each other easily?
Precisely. Yeah, good analogy. But then things changed. We saw a real game changer with these multimodal large language models, or MLLMs.
Yeah.
MLLMs, right?
The key thing here is they're end-to-end systems. They process everything together in one go. And they're built around language as this sort of central hub for understanding.
Ah, okay.
And this led to huge leaps in tasks like, say, looking at a picture and answering questions about it. Visual question answering. These models started nailing things like visual common sense reasoning, too.
Common sense reasoning.
That's
So not just what's in the picture, but the implied stuff.
Exactly. The unspoken common sense stuff. And, yeah, visual question answering, too. The research we're looking at mentions specific examples, showing how far it's come over the years.
That sounds like a massive step. But were these early MLLMs, like, perfect? What were the teething problems?
No, definitely not perfect. They had limits, for sure, especially with more complex reasoning.
Like what?
Well, things like generating new hypotheses on the fly or following a logical argument with multiple steps, that could be really tough for them. They're often good at spotting patterns they'd seen before, but maybe not so much at, deeper understanding. So they could tell you maybe what is in a picture, but not explain the whole story behind it in a nuanced way.
Exactly right. And that's where this really clever idea came in, called chain of thought reasoning. COT for short.
Chain of thought. Oh,
Yeah, this was a breakthrough because it allowed the models to actually show their thinking step by step instead of just giving an answer.
They show their work, like in math class.
Kind of, yeah. They explained the intermediate steps they took. And this didn't just make their answers more accurate sometimes. It also made their reasoning much, much clearer for us humans to understand. Made them more interpretable.
That makes total sense. Like explaining your logic out loud when you solve a puzzle. It helps you and it helps others follow along.
Absolutely. So where are we now? The big push is towards AI systems that are even more unified, more adaptable, and can truly reason across all these different information types, fluidly.
Okay, so the paper, it breaks down this development into 3 main stages. Let's dig into the first one. Perception-driven modular reasoning. What was that about?
Right. So this early stage, it was really about building those specialized tools like we talked about, separate modules for different tasks.
Okay.
The focus was on putting in things like attention mechanisms so that AI knows what parts of the input are important, memory, of course, and compositionality. That's the ability to put different bits of information together meaningfully.
So still kind of separate parts, but each part getting smarter on its own.
Exactly. And the huge moment here was the transformer architecture. That really changed
The
things.
transformer, right? That's everywhere now.
It is. And that, along with techniques like pre-training on huge data sets and then fine-tuning, well, it dramatically improved how visual and text information could be brought together. These transformer models got much better at aligning and combining different data types right from the get-go.
Okay. And within this first stage, there were a couple of main ways they did it. The paper mentions dual encoder contrastive reasoning. What's that?
Yeah, so think of dual encoder models like having separate pathways, one for seeing, one for reading,
Two
maybe.
streams.
Two streams, exactly. And the contrastive reasoning part is like teaching the AI which ideas match up across those streams. It learns to pull representations of related things closer together in this sort of abstract space and push unrelated things apart.
Okay, like matching concepts.
Yeah, precisely. A great example is CLIP. It used this to build a shared understanding between images and text. And that allowed it to do something really cool called zero-shot reasoning. It could understand and categorize images based on text descriptions it had never explicitly been trained on together.
Wow. Okay, so it learned the underlying meaning.
That was the key insight, yeah. Creating that shared space gave it amazing flexibility.
Okay, so two streams learning a common language. What about the other approach? Single transformer backbone interactive reasoning. Sounds different.
It is different. Instead of separate paths, this approach tried to integrate everything visual, textual, right into one single unified transformer network.
All in one pot.
Pretty much. The idea was to have them interact and influence each other from the very beginning. Visual BERT is a key example here, combining vision and text inputs in one transformer. What's really interesting is how different models played with this. Like Cosmos 1 could handle text and images mixed together, interleaved in the input.
Like reading a web page with pictures in it.
Exactly, a big step towards unified processing. And then Cosmos 2 got much better at grounding, figuring out precisely which object in an image you're talking about in the text.
Okay, that feels like a tighter integration. So let's move to stage 2. Language-centric short reasoning. The paper calls it System 1 reasoning. What's the shift here?
Right, this stage is really defined by those MLLMs we mentioned earlier becoming dominant. And these models started showing what we call emergent reasoning abilities.
Emergent, like they could suddenly do it without specific training for that task.
Kind of, yeah. But the paper points out this reasoning was often, let's say, shallow, more based on pattern recognition than deep step-by-step logic, like intuitive thinking, System 1.
So they could reason a bit, but maybe couldn't explain how very well or handle really complex stuff?
Exactly. And that's where multimodal chain of thought, MCT, became so important. It took that Cavati idea and stretched it to handle language and other data types.
Ah, applying Cavati to multimodal?
Yes. By making the intermediate steps explicit, MCT helped align the different modalities better, integrate knowledge more effectively, and sort of ground the reasoning in the actual data. And the cool thing, often didn't need tons of new training data or totally new model designs.
Okay, making the thinking visible, even with pictures and sounds. The paper breaks down stage 2 approaches: prompt-based MCT, structural reasoning, and externally augmented reasoning. Let's start with prompts. How does prompt-based MCT work?
So think of prompts as really carefully written questions or instructions. They guide the AI,
Like giving it directions.
pretty much. Prompt-based MCT uses these to nudge the MLLM to break down a problem into smaller steps, especially when dealing with multiple data types. We've seen this used in lots of areas, like video understanding. Models like VOT use scene descriptions over time to guide the AI from just seeing what's there to understanding the bigger picture, the narrative.
I see.
Video Agent uses prompts for an LLM to strategically pick out key moments in long videos, like finding clues. And LET prompts the AI frame by frame to track changes.
So the prompt is like a little helper guiding the reasoning for different kinds of media.
Exactly. And not just video. PKRDOT uses prompts for self-driving car AI, structuring how it thinks about what it sees and what decisions to make. LPE uses prompts on speech and emotional cues to make responses more empathetic. Even for object detection, like KennyDet, or figuring out actions in video, like AntGPT, good prompts have been really key.
Very flexible. Okay, what about structural reasoning? How's that different from just using prompts?
Structural reasoning goes a step further. It gives the AI predefined patterns or frameworks to follow.
Like a template.
Yeah, exactly. Instead of just relying on how you ask the question, it sets up a more rigid structure for the thinking process. Often involves something called rationale construction, how the AI learns to explain why it reached a conclusion.
Ah, generating the explanation.
Right. Multimodal CT, for instance, actually separates generating the explanation from making the prediction, which can cut down on errors. Other work, like T-Psych, showed the quality of these AI explanations is crucial for getting the right answer. And in self-driving, GCA explicitly links explanations to sensor data and past experiences for more reliable reasoning.
So it's like giving the AI a specific thinking routine for certain problems.
You got it. And you see this in models like BDAG, which has AI agents basically debate possibilities to find the best conclusion. COT-DET, which we mentioned with prompts, also has a structural element using affordance analysis, thinking about what an object can do to help identify it. Models like Shikra and ECOT also fit here, focusing on combining reasoning with perception and action effectively.
Interesting. Feels like a move towards more organized, maybe more reliable AI thinking. The third category in stage 2, externally augmented reasoning. What's that?
Right. This is where we give the AI access to tools or information outside its own internal knowledge.
Like giving it a calculator or letting it search the web.
Exactly like that, but often more sophisticated tools. This lets it tackle harder problems by using a wider range of resources. One way is search algorithm enhanced MConT. Instead of just one line of thought, these methods use search algorithms to explore multiple reasoning paths.
Exploring possibilities.
Yeah. MMTOT uses advanced models and search to find the best multimodal outputs. HOT creates these interconnected thoughts from different data types. AGOT built a whole network of reasoning steps, pulling in visual info at each stage. And B2G, with its agent debate, also fits here by exploring different ideas.
So it's like letting the AI brainstorm and weigh different options before settling on an answer.
Precisely. And then there are the actual tools,
Yeah.
specific external modules the MLLM can call on.
Like plugins.
Kind of. L3GO, for instance, can use software like Blender to generate 3D objects. HYDRA uses AI agents learning through trial and error for complex visual reasoning. DEDCOT uses visual hints to focus on the right things for object detection. Chained Image can even generate intermediate images as part of its reasoning.
Wow, generating pictures to help it think.
Yeah. Animal focuses on efficiency and bringing data together, and SECMRN uses language structure to understand images better.
That's a serious toolkit. And finally, under external augmentation, RA, retrieval augmented generation. We hear about RAG for chatbots. How does it apply here?
Well, the core idea is the same. Let the AI pull in relevant info from outside sources to improve its answers or reasoning. But multimodally, it can retrieve not just text, but images, videos, structured data. So RAGAR uses it to fact-check political claims, finding evidence in different formats. Chain of Action retrieves info from all sorts of places using structured steps. Camcode uses knowledge graphs, basically structured databases of facts, to boost its multimodal reasoning. ARMCTS combines real-time retrieval with that sophisticated MCTS search we'll touch on again, grabbing knowledge at each step. MRMKG uses knowledge graphs that already contain multimodal info. It's all about giving the AI a much bigger, richer knowledge base across formats to draw upon.
So ARAG gives these modders access to a vast library, including different media types, making their reasoning potentially much better informed. Okay, let's shift gears. Stage 3, language-centric long reasoning. System 2 thinking and planning sounds like a big step up.
It absolutely is. This stage is about moving towards more deliberate, step-by-step, sustained reasoning for really challenging tasks. Deeper thinking, exactly. Extending those reasoning chains, often using supervision or reinforcement learning to guide the process. A huge focus here is cross-modal reasoning itself, truly integrating and reasoning across text, images, video, etc. The paper stresses it's not just about using text to understand other stuff, but really blending them, either intrinsically within the model or using those external tools. The goal is more accuracy, more reliability by dynamically pulling in relevant info from different places.
Moving beyond just answering a simple question about a picture to really understanding the complex interplay over time, maybe. And the paper mentions multimodal O1. What's that?
Right, so with all the buzz around OpenAI's advanced reasoning models like GPT-4o, there was a big push to get similar capabilities into more open models. This led to these multimodal O1 models like Marco O1 Llamaberry. They use chain of thought. But the key is that fine-tuning them specifically on code data seems to tap into a more deliberate, slower, System 2 way of thinking. Compared to earlier coding, this helps them tackle complex, open-ended questions better, partly by giving them ways to reflect on their own thinking and fix errors. Models like Lavacode, LlamaVO1, Redstar, Mulberry, they're extending this more thoughtful style to multimodal problems. Instead of just think-answer, they often use a more detailed structure like summary or rationale, then caption, then thinking, then answer.
A more structured, multi-stage process designed for handling different data types more deeply. And you mentioned planning algorithms. like MCTS.
Yes, exactly.
Yeah.
Some of these multimodal O1 models are integrating sophisticated planners like Monte Carlo tree search, MCTS.
Monte Carlo research. Okay.
It's a powerful search technique. Helps the AI explore different potential solution paths much more effectively than simpler methods. Models like Marco O1, LlamaBerry, and Mulberry have successfully used MCTS to guide how they generate their reasoning steps. Leads to more refined answers.
It really sounds like a significant evolution towards more robust and sophisticated multimodal reasoning. Now, the paper introduces this really cool idea. Native Large Multimodal Reasoning Models, NLMRMs. This sounds like the next frontier. What's the vision?
Yeah, NLMRMs, the core idea is a shift. Instead of adding reasoning onto language models, the reasoning ability would emerge natively from the AI's capacity for uh, omnimodal perception, understanding through all senses, and goal-driven cognition, its drive to achieve goals.
So reasoning isn't bolted on, it's baked in from the start.
Exactly. It's about building AI where understanding and reasoning across all data types is fundamental, not an add-on feature.
That feels like a really profound change in how we approach AI.
Right.
The paper highlights two key capabilities for these NLMRMs, multimodal agentic reasoning and omnimodal understanding and generative reasoning. Let's break those down. What's multimodal agentic
All
reasoning?
right, so imagine AI systems that don't just passively understand, but can proactively interact with their environment to achieve goals.
Yeah.
That's agentic reasoning.
Taking action.
Taking action. It involves breaking down complex goals into steps, adapting plans on the fly based on new sensory input, and crucially, learning from direct experience in the world. Embodied learning.
So AI that not only understands through multiple senses, but also acts and learns from those actions in a rich multimodal world. Wow.
Yeah. And the second capability is omnimodal understanding and generative reasoning. This is about the AI seamlessly processing and creating information across all data types using a unified internal representation.
Unified representation. Key
A
idea.
very key. Taking in diverse inputs, seeing, hearing, reading, combining it into deep understanding, and then being able to generate outputs in whatever format is needed, text, image, sound, whatever.
Incredibly powerful. A truly integrated intelligence. The paper mentions current models are exploring bits of this, but haven't quite put it all together yet.
That's right. We see advanced models doing amazing things, identifying locations, solving visual puzzles, creating multimedia, but they often still struggle with sustained back-and-forth reasoning and fully combining that proactive, goal-driven behavior with truly unified omnimodal understanding.
And it sounds like there are specific tests, benchmarks, designed to really push them on this omnimodal front.
Oh, yeah. Benchmarks like OmniMI, OmniBench, Task Anything, Judge Anything, Mix of All X. They're designed specifically to test this unified understanding and reasoning across many modalities.
And how do current models do?
Well, what we often see is a performance drop. Even the best models can struggle when a task really requires blending understanding from different senses simultaneously, compared to tasks involving just one modality. Even models like OpenAI's O3, while impressive, still show limitations in consistent interactive reasoning across diverse modalities, especially on tough benchmarks like BabbleBench or Omixar or Taskle's audio-video question answering.
So huge progress, but that final leap to true NLMRMs is still a major challenge. What are the key technical hurdles and, I guess, the exciting research directions?
The paper highlights several big ones. A fundamental challenge is creating those unified representations and achieving seamless cross-modal fusion. Moving beyond separate encoders for each sense towards a single integrated architecture that can handle and generate diverse modalities coherently.
The holy grail, almost.
Kind of, yeah. We're seeing progress, though. Early work like AnyGPT using discrete representations, and more recently, models like Bechuan Omni 1.5 or Quinn 2.5 Omni with clever techniques like time-aligned multimodal ROP. They're pushing in this direction.
Finding that common internal language. What else?
Another huge piece is learning from world experience. For native multimodal reasoning, AI needs to learn continuously from real-world interaction, handling long, complex multimodal reasoning chains, coordinating multiple tools over time. That's tough.
Like how we learn by just living and doing.
Exactly. And tied to that is data synthesis. High-quality training data is crucial. To push models towards complex tasks, aligning 3 or more modalities, interactive QT, visual generation, multi-step planning, coordinating tools, we need better ways to create the data they learn from. Current synthesis often focuses on simpler aspects.
Right. The learning materials have to match the ambition. Finally, the paper mentions datasets and benchmarks. Sounds like a whole ecosystem is needed to drive progress.
Absolutely essential. The paper organizes them nicely into understanding, generation, reasoning, and planning.
Okay.
For understanding, you have benchmarks for visual stuff, general VQA, multilingual VQA, broad tests like Bench, and audio stuff speech, general audio like Clotho, music like MusicNet, comprehensive ones like VoiceBench.
So tests for how well they perceive different senses. What about the other areas?
Generation benchmarks test, creating new content across modalities. Text-to-image like MSEO-Woo, text-to-video like Vigen1M, even text-to-interleaved image text. Reasoning benchmarks cover general visual reasoning like VCR, broad intelligence tests like MMMU, even specific domains like diagrams, math, physics. And planning looks at things like navigating web interfaces or acting in simulated environments like MindDojo or Habitat.
Wow, it's a really comprehensive toolkit researchers use to measure progress and, well, figure out what to build next.
Precisely. They're crucial for identifying weaknesses and guiding where the field goes next in this quest for truly capable multimodal reasoning.
Well, this has been incredibly insightful, a real deep dive into multimodal reasoning. Just to quickly recap, we've seen AI move from separate senses to unified models. Chain of thought was a huge step for making reasoning explicit. And now this vision of native large multimodal reasoning models, NLMRMs, points towards AI that perceives, understands, and reasons much more naturally, much more like us perhaps.
Exactly. NLMRMs really represent a potential fundamental shift towards AI, where comprehensive perception, precise understanding, and deep reasoning are just core capabilities built in.
And it brings us to a final thought for you, the listener. Just consider, what happens when AI can reason seamlessly across all senses, sight, sound, maybe even touch or others, and learn directly from interacting with the world? How could that fundamentally change how AI works with us and maybe changes the world itself? What new possibilities and, yeah, maybe what new challenges arise as these native systems get more sophisticated? Definitely something to chew on.
Good question.
Thanks for joining us on this deep dive.